Every second, the universe is tearing itself apart, growing faster than light can chase it. We know this. What we cannot agree on is how fast. Two groups of scientists, both brilliant, both careful, both getting different answers. And a Nobel Prize winner just proved neither side made a mistake. We will travel from the oldest light in existence to dying stars used as measuring tape to a telescope that sees 130 million light years away and still finds the same impossible gap. If you enjoy the journey, like and subscribe. It helps more than you know. Brace yourselves. We begin. Picture the universe like a loaf of bread rising in an oven. Every raisin inside moves away from every other raisin as the bread puffs up. The raisins are not moving on their own. The bread itself is growing. That is exactly what space does. Every galaxy is being carried away from every other galaxy, not because they are flying through space, but because space itself is stretching. Scientists have known this since the 1920s. A man named Edwin Hubble pointed his telescope at faint smudges of light in the night sky and realized they were entire galaxies, sitting millions of light years away, and every single one of them was moving away from us. The farther away a galaxy was, the faster it moved. Space was expanding. That discovery changed everything. But here is where the story gets strange. To understand the universe, scientists need to know exactly how fast it is expanding. That single number controls everything. It tells us how old the universe is. It tells us what the universe will look like in 1 trillion years. It tells us whether everything we think we know about physics is correct. So scientists measured it carefully with the best tools they had. And they got two different answers. One group looked at the oldest light in the universe, radiation left over from the Big Bang itself, still traveling through space like a ghost from the beginning of time. They calculated an expansion rate from that ancient signal. Their answer was precise. Their math was solid. Their result pointed to a universe expanding at roughly 42 miles per second for every 3.25 million light years of distance. That is already hard to picture. Space stretching by 42 miles every second, and that number grows the farther out you look. The second group took a completely different approach. Instead of looking at ancient light, they looked at nearby galaxies. They studied stars with known brightness, stars that pulse and dim in a rhythm you can measure from across the universe. Using those stars as rulers, they climbed outward through space step by step. Their answer: the universe is expanding closer to 46 miles per second per the same distance. That gap sounds small. It is not. Written out across the full scale of the universe, the difference between those two numbers means either our understanding of the early universe is broken, our tools for measuring nearby galaxies are wrong, or something in the laws of physics itself is missing. And here is what made the whole scientific world stop cold. For years, the most popular explanation was simple human error. The nearby galaxy team was probably making a mistake. Their telescopes were good, but maybe not good enough. Maybe they were miscounting stars. Maybe something was distorting the light. The early universe team had the more elegant math. Everyone assumed the gap would close once better technology arrived. Then the James Webb Space Telescope launched. And the gap did not close. The most powerful telescope ever built confirmed the nearby galaxy measurements were right all along. No error, no mistake. Two correct answers. Two different speeds. A Nobel Prize winner looked at the data and said, out loud, that we may have misunderstood the universe entirely. That is where we are right now, standing at the edge of everything we thought we knew, staring at a crack in the foundation of physics that nobody knows how to fix. And the deeper you go into the story, the stranger it gets. Imagine you are standing in the middle of a city, and every building around you is slowly drifting away. The building 1 block over moves slowly. The building 10 blocks away moves much faster. The building 100 blocks away is practically sprinting. And every single building follows the exact same rule: double the distance, double the speed. The city itself is expanding, and the rule governing that expansion can be described by a single number. That number is the Hubble constant. It tells us the relationship between distance and speed in an expanding universe. Pick any galaxy, measure how far away it is, Multiply that distance by the Hubble constant, you get the speed at which that galaxy is moving away from us. The formula sounds simple. The consequences are enormous. If the Hubble constant is large, the universe is expanding fast. A fast expansion means the universe is younger than we thought, because it took less time to reach its current size. A fast expansion also means dark energy, the mysterious force pushing everything apart, is stronger than expected. A fast expansion changes our prediction for how the universe ends. If the Hubble constant is small, the opposite follows. The universe expanded slowly, aged longer, and dark energy plays a quieter role. Every cosmology textbook, every physics lecture, every calculation about the universe's past and future depends on this number being correct. And right now, we have two versions of this number, and they refuse to match. Scientists call this the Hubble tension. The word tension sounds polite. What it actually represents is a crack running through the entire foundation of modern physics. Two methods of measuring the same thing keep producing results that disagree by about 9%. 9% sounds small. Across the scale of the universe, 9% is a chasm. Here is the thing about 9% that most people miss. Physics equations do not have a slot for close enough. Either the universe follows a set of rules or it does not. Either our model of reality is complete or it has a missing piece. A 9% disagreement is the universe telling us loudly and clearly that something is wrong with the rulebook. The Hubble constant carries another weight too. It is used to calculate the age of the universe. Right now, the most widely accepted age is around 13.8 billion years. But that number was calculated using the slower expansion rate from the early universe measurements. If the faster nearby galaxy measurement is correct, the universe is younger than we think, by potentially over 1 billion years. Every timeline we have built, every story we tell about how stars formed and galaxies grew, shifts. One number, two answers, a universe waiting for us to figure out which version of physics is real. Edwin Hubble discovered the expansion in the 1920s. The constant was named after him. He never imagined that nearly a century later, his discovery would be at the center of the biggest crisis in modern astronomy. The scientists trying to resolve this tension split into two camps, each convinced their method is correct, each backed by decades of careful work, and each now forced to admit that the other side made no obvious mistake. Something else is causing this, something deeper. And to understand what that something might be, you need to go back to the very beginning, back to the moment the universe was born, and the faint glow it left behind that scientists are still reading today. Roughly 13.8 billion years ago, everything that exists exploded into being from a single point, smaller than anything you can imagine. The temperature was so extreme that matter itself could not form. Atoms could not exist. Electrons and protons flew free, colliding constantly, turning space into an opaque, glowing fog. Light tried to travel but bounced off particles almost instantly, trapped inside the chaos. For 380,000 years, the universe stayed that way. Hot, dense, glowing, but sealed. Then something happened. The universe cooled just enough. Electrons slowed down and finally bonded with protons. Atoms formed for the first time, and suddenly, light had a clear path to travel. In an instant spanning the whole universe, the fog lifted. Every point in space released a burst of light, all at once, in every direction. That light is still traveling today. After nearly 14 billion years of journeying through expanding space, it has been stretched so far that it dropped below what human eyes can see. It shifted out of visible light and became microwave radiation. Scientists call it the cosmic microwave background. You can think of it as the cooling ember of the Big Bang, a faint warmth still spreading outward from that original explosion, now filling every corner of the sky. Here is the part that should make your jaw drop. This radiation is everywhere. Every direction you point a sensitive antenna, the signal is there. Astronomers in the 1960s accidentally discovered it while trying to troubleshoot noise in a communications antenna. They kept picking up a faint hiss coming from all directions equally. They thought it was pigeon droppings inside the antenna. They cleaned it. The hiss remained. Eventually, they realized what they were hearing, the literal sound, translated into radio waves, of the universe being born. The cosmic microwave background is a photograph, a single image of the universe at 380,000 years old, before any stars, before any galaxies, when the cosmos was still a smooth, almost perfectly uniform sea of cooling gas. Scientists can read it like a map. The tiny temperature differences across this ancient glow tell us how matter clumped together, how gravity pulled those clumps into the first stars, how those stars eventually became the galaxies we see today. And buried inside this map is a prediction, a precise mathematical prediction for how fast the universe should be expanding right now. Scientists applied the standard rules of physics to the microwave background data and calculated an expansion rate. That rate became one side of the Hubble tension debate. It is a careful, well-tested prediction built on some of the most solid physics we have. The problem is, when astronomers go outside and actually measure the expansion happening in the universe today, they get a faster number. The universe right now seems to be moving faster than the baby photo of the universe said it should. Either something accelerated the universe between then and now, something our models do not account for, or our models are missing a piece of physics entirely. The next clue comes from a satellite launched not to photograph the sky, but to take the temperature of the universe itself. In 2009, the European Space Agency launched a satellite the size of a small van into deep space, positioned about 1 million miles from Earth. Its job was precise and enormous: map the entire cosmic microwave background with more detail than any instrument had ever achieved. Scientists named it Planck, after the German physicist who helped build the foundations of quantum theory. Planck spent 4 years scanning the sky. Over and over, it mapped the temperature of the oldest light in the universe down to differences smaller than a millionth of a degree. The result was the most detailed portrait of the early universe ever created, a full sky image showing the faint ripples in temperature that seeded every galaxy, every star, and every planet that exists today. Planck released its first major results in 2013. The scientific community treated it like a revelation. Here was the universe at 380,000 years old, frozen in extraordinary detail. Scientists fed the Planck data into the standard model of cosmology, which is the set of equations that describes how the universe grows, cools, and changes over time. The model is built on Einstein's equations, quantum physics, and decades of astronomical observation. It is the closest thing physics has to a complete instruction manual for the universe. The calculation produced a clean answer. The universe should be expanding at about 42 miles per second for every 3.26 million light years of distance. That distance unit, 3.26 million light years, is called a megaparsec. Astronomers use it the same way road signs use miles. It is just the most convenient unit for measuring cosmic distances. 42 miles per second per megaparsec. Write that down. It becomes the center of everything. This number carried enormous credibility. The Planck satellite was the most precise instrument of its kind. The standard model of cosmology had survived every test thrown at it for decades. Scientists trusted this result the way engineers trust the blueprints for a bridge that has stood for 100 years. And then the other team published their number, 46 miles per second per megaparsec, from actual observations of real galaxies close enough to measure directly. 4 miles per second difference. Across the scale of the universe, that gap means the cosmos is expanding about 9% faster than the early universe prediction says it should. A 9% disagreement between theory and observation in physics is serious. Structures are not supposed to crack by 9% without a reason. The Planck result told us what the universe was. The nearby galaxy measurement told us what the universe is. And those two descriptions do not match. One possible explanation was immediately obvious to everyone. Maybe the nearby galaxy team was wrong. Measuring stars across millions of light years is brutally difficult work. Space dust blurs the view. Stars crowd together and overlap. Tiny errors in one step of the measurement compound into larger errors by the end. The Planck data looked clean, the predictions looked solid. For years, most physicists assumed the tension would resolve itself once someone found the measurement error hiding in the nearby galaxy data. Nobody found it. And the method the nearby galaxy team relied on, the technique that produced their faster number, is one of the most elegant tricks in all of science. Measuring distance in space is one of the hardest problems in science. You cannot drive there and check the odometer. You cannot bounce a signal off a distant galaxy and wait for the echo. Light from some galaxies takes billions of years to reach us. By the time it arrives, the galaxy has moved. Everything is always moving, always changing, always uncertain. So astronomers built a system, a series of overlapping methods, each one reaching a little farther than the last, each one relying on the step before it. Scientists call it the cosmic distance ladder. Every rung uses a different trick to measure distance, and each rung has to be calibrated precisely before the next one can be trusted. The first rung is the closest. Parallax. Hold your finger in front of your face and close one eye, then the other. Your finger appears to jump against the background. That apparent jump is caused by the difference in position between your two eyes. Astronomers do the same thing with Earth itself. They photograph a nearby star in January, then photograph the same star in July when Earth is on the opposite side of its orbit. The star appears to shift slightly against the background of farther stars. By measuring that shift, astronomers can calculate the star's exact distance. This works for stars up to a few thousand light years away. After that, the distances get too large for parallax to work. Stars too far away show no measurable shift at all. So astronomers need the next rung. Enter Cepheid variable stars. These are stars that pulse. They swell and shrink, brighten and dim on a clock-like schedule. A Cepheid that takes 10 days to complete. One pulse is always a certain true brightness. A Cepheid that takes 30 days is brighter still. The rhythm is the key. Once you know the rhythm, you know the true brightness. Once you know the true brightness, you can compare it to how bright the star looks from Earth. The dimmer it looks, the farther away it must be. Cepheids allow astronomers to measure distances out to tens of millions of light years. But tens of millions of light years is still a small slice of the universe. To measure expansion across the full cosmos, astronomers need to reach hundreds of millions, even billions of light years out. That requires one more rung. Type Ia supernovae. These are explosions, specific, predictable, violent explosions. When certain stars reach a critical mass, they detonate in a nuclear blast so powerful that for a few weeks, a single star outshines an entire galaxy. Type Ia supernovae always detonate at roughly the same mass, which means they always produce roughly the same peak brightness. An explosion a billion light years away looks dimmer than one 100 million light years away. By measuring exactly how dim, astronomers calculate exactly how far. Each rung of this ladder depends on the one below it. Parallax calibrates the Cepheids calibrate the supernovae. The supernovae reach the edge of the measurable universe. If any rung has a flaw, the whole ladder tilts. And critics suspected exactly that. Picture a star the size of a school bus lot. Now picture it breathing, slowly expanding outward, brightening as it swells, then contracting, dimming as it shrinks, then swelling again, expanding and contracting, brightening and dimming, over and over on a perfect schedule. Days pass between each pulse, sometimes weeks. The rhythm never breaks. These stars are called Cepheid variables, and for over a century, they have been the most powerful measuring tool in astronomy. The discovery that made Cepheids useful happened in the early 1900s. An astronomer named Henrietta Swan Leavitt was cataloguing stars in a nearby galaxy and noticed something remarkable. Certain stars pulsed, and the ones that pulsed more slowly were always brighter than the ones that pulsed quickly. There was a direct mathematical relationship between the period of the pulse and the true brightness of the star. Every time. No exceptions. This is called the period luminosity relationship. In plain terms, if you can measure how long a Cepheid takes to complete one pulse, you know exactly how bright it truly is. That single fact turned pulsing stars into cosmic rulers. Here is how astronomers use them. A Cepheid in a distant galaxy pulses over a certain number of days. From that pulse period, scientists calculate the star's true brightness the same way you can figure out how powerful a light bulb is from its wattage label. Then they look at how bright the star appears in the telescope. The difference between true brightness and apparent brightness reveals the distance. A star that should be blindingly bright but appears dim must be very far away. The math is clean, the physics is solid. Astronomers have used Cepheids to measure distances to hundreds of galaxies. The technique works spectacularly well, up to about 100 million light years away. But here is the problem hiding inside that process. Cepheid variables live inside galaxies. Galaxies are crowded places. Stars packed together, especially near the center of a galaxy. When a telescope looks at a distant galaxy and spots a Cepheid, the light reaching the sensor is sometimes a blend of the Cepheid and the stars immediately around it. Neighboring stars leak light into the same pixel. The Cepheid appears slightly brighter than it really is. If a star looks brighter than it truly is, you calculate that it is closer than it truly is. Pull that error through to the final expansion rate, and the speed of the universe comes out too high. This is the crowding problem, and for years, it was the most popular explanation for why the nearby galaxy expansion rate was faster than the early universe prediction. The critics were not being dismissive. They were being scientifically careful. The Hubble Space Telescope, brilliant as it was, has a mirror just over 7 feet wide. Resolving individual stars in a galaxy 60 million light years away, separating a faint Cepheid from its glowing neighbors, push that mirror to its absolute limit. Scientists on both sides of the debate agreed the only way to settle the crowding question was a telescope with a much bigger mirror, one capable of seeing individual stars with perfect clarity across tens of millions of light years. That telescope was already being built, and what it found when it looked at those Cepheids was the last thing most physicists expected. Some stars die quietly. They cool, dim, and fade over billions of years until nothing remains but a dim cinder drifting through space. Other stars go out with an explosion so violent that for a few days, a single dying star produces more light than an entire galaxy of hundreds of billions of stars. Astronomers call these supernovae, and one specific type of supernova turned out to be one of the most precise measuring tools in the history of science. A type Ia supernova begins with a dead star called a white dwarf. After a star like our sun burns through its fuel, it collapses into a white dwarf, roughly the size of Earth, but containing the mass of the entire sun. White dwarfs do not burn. They just sit there, dense and cooling, held up by the pressure of tightly packed electrons. But some white dwarfs are not alone. They orbit a companion star, and over millions of years, they steal material from that companion, pulling gas off it like a vacuum slowly draining a swimming pool. The white dwarf gains mass, slowly, steadily, until it crosses a specific threshold. 1.4 times the mass of the sun. That is the critical limit. Past that point, the electron pressure holding the white dwarf up can no longer resist gravity. The star collapses in an instant and then detonates in a thermonuclear explosion. The entire star tears itself apart in a matter of seconds. Here is the crucial detail, because every type Ia supernova detonates at almost exactly the same mass. Every explosion releases almost exactly the same amount of energy. The peak brightness is nearly identical across every type AI event, no matter where in the universe it happens. Scientists call them standard candles, objects with a known true brightness that can be used to calculate distance. The dimmer a type Ia supernova appears, the farther away it is. By measuring the brightness, astronomers get the distance. Clean, reliable, repeatable across billions of light years. The power of this method is that it works at ranges far beyond what Cepheid stars can reach. Cepheids top out at about 100 million light years. Type Ia supernovae are visible across billions of light years. They extend the cosmic distance ladder into the deep universe. And in 1998, 2 independent teams used this method to make a discovery so shocking it earned a Nobel Prize. They expected the universe's expansion to be slowing down. Gravity should be pulling everything back together, gradually putting the brakes on the Big Bang's initial push. Instead, the supernovae showed the opposite. The expansion of the universe was speeding up. Something was pushing galaxies apart faster and faster over time. That something was dark energy, unknown, invisible, filling all of space, and apparently winning a tug of war against gravity on a cosmic scale. One of the scientists leading that discovery was a young astronomer named Adam Rees. He would go on to use both Cepheids and supernovae in the research that sits at the very center of the Hubble tension story. His work earned him a Nobel Prize in 2011, and it planted a mystery that the most powerful telescopes in human history still have not solved. In the late 1990s, two teams of astronomers were racing to do the same thing. They wanted to measure how quickly the expansion of the universe was slowing down. Everyone assumed it was slowing. Gravity pulls matter together. After the Big Bang pushed everything apart, the combined gravity of all the matter in the universe should have been gradually applying the brakes. The question was simply how fast those brakes were working. Adam Rees was a young researcher on one of those teams. He analyzed data from distant Type 1a supernovae, those precisely predictable stellar explosions that work as cosmic measuring tape. His job was to compare how bright these supernovae appeared to how bright they should be, based on the physics. The numbers came back wrong. The supernovae were dimmer than expected, not by a tiny amount. By enough to mean they were farther away than they should have been. And the only explanation for galaxies being farther away than models predicted was that the universe was expanding faster than expected, and had been for billions of years. Rees ran the numbers again. The result held. He brought the findings to his team. Then they went to the second competing team, which had been running the same analysis. Both groups had found the same thing, working completely independently using different supernovae samples. The expansion of the universe was accelerating. This flew against everything physicists believed. Gravity was supposed to dominate at large scales. A universe full of matter should be gradually slowing down, not speeding up. For the universe to accelerate, something had to be pushing outward against gravity across every point in space simultaneously. That something became known as dark energy. Scientists did not discover what dark energy is. They discovered what it does. It fills space, it pushes everything apart. And over billions of years, it has been winning. The announcement in 1998 was a scientific earthquake. Textbooks were wrong. Models were incomplete. Physics itself had a new mystery sitting at the center of it. Rees, his colleague Brian Schmidt, and Saul Perlmutter from the competing team shared the Nobel Prize in Physics in 2011 for this discovery. The prize recognized one of the most important astronomical findings in history. The universe is not just expanding, it is accelerating. But here is what made Rees different from many scientists who win major prizes and then settle into a comfortable career. He kept pushing. He turned his attention to the Hubble constant, the number measuring the current expansion rate. He wanted to pin it down with precision. Using Cepheid variable stars and Type 1 supernovae together, he built a measurement chain stretching across hundreds of millions of light years. His results kept coming back faster than the early universe prediction. Every time he refined the measurement, every time he added more data, the number stayed stubbornly high. Around 46 miles per second per megaparsec, refusing to drift down toward the 42 that the cosmic microwave background predicted. The tension was real. He was sure of it. Others were not, and the debate was about to reach a breaking point. Winning a Nobel Prize is supposed to be an ending. The moment a career of work gets recognized, celebrated, and filed into the permanent record of human knowledge. For Adam Rees, it was the opposite. The prize put a spotlight on a problem his research had accidentally created, and that problem was growing larger every year. The Nobel Committee awarded Rees, Schmidt, and Perlmutter for discovering that the expansion of the universe was accelerating. That discovery implied dark energy existed. Dark energy went into the standard model of cosmology as a parameter, a number plugged into the equations to account for the acceleration. Scientists called this parameter lambda from Einstein's cosmological constant, which Einstein himself had introduced and then famously abandoned as a mistake. Turns out Einstein's mistake was right all along. The standard model absorbed dark energy, equations were updated, cosmologists celebrated. The model now had 5 major ingredients: ordinary matter, which makes up stars and planets; dark matter, invisible mass that holds galaxies together; dark energy, the force pushing the universe apart; radiation, including ancient light; and the geometry of space itself. Scientists called this the lambda-cold dark matter model. Physicists called it the most successful description of the universe ever built. And it worked beautifully. For a while, the Planck satellite mapped the cosmic microwave background in exquisite detail and fed data into the lambda-cold dark matter model. Out came a precise expansion rate, 42 miles per second per megaparsec. The model predicted the universe's expansion with stunning accuracy, tracing the history of the cosmos from a fraction of a second after the Big Bang to today. Except the local universe did not agree. Rias was using Cepheid stars and supernovae to measure the expansion rate in our cosmic neighborhood, galaxies within a few 100 million light years, and his numbers kept landing around 46 miles per second per megaparsec. The gap between 42 and 46 was the Hubble tension, and it was not going away. Winning the Nobel Prize made Rias one of the most listened to voices in astrophysics. When he said the tension was real, people paid attention. When he said the standard model might be incomplete, the scientific community could not dismiss it easily. He had a Nobel Prize, a track record, and 2 decades of careful measurements backing him up. Other researchers started joining the debate. Some supported Rias, others argued the measurement was flawed. Papers multiplied, conferences filled with arguments. The tension became the defining problem of modern cosmology. The scientific community agreed on one thing. The only way to settle the argument was a telescope powerful enough to eliminate the most likely sources of error. A telescope that could see individual Cepheid stars with perfect clarity, even inside crowded, dusty galaxies tens of millions of light years away. That telescope launched in 2021. It carried the hopes of both sides of the debate, and what it found permanently changed the direction of physics. Here is the simplest version of the problem. 2 teams of scientists, 2 methods, 2 answers. Team 1 looks backward in time. They study the cosmic microwave background, the ancient light left over from the Big Bang. They feed that data into the best physical model of the universe ever built. They get an expansion rate of about 42 miles per second per megaparsec. Team 2 looks at the universe right now. They study Cepheid stars in nearby galaxies. They measure real distances to real galaxies using real starlight. They get an expansion rate of about 46 miles per second per megaparsec. 4 miles per second difference, roughly 9%. That gap is the Hubble tension. To understand why 9% is catastrophic, consider what physics actually is. Physics is the attempt to describe the universe with equations precise enough to make predictions. Those predictions get tested against observations. If the prediction and the observation match, the equation stands. If they disagree by 9%, something in the equation is wrong. The standard model of cosmology has survived every test thrown at it for decades. Galaxy distributions, the behavior of cosmic radiation, the abundance of light elements in the universe, all of it lines up beautifully with the model's predictions. And then comes the Hubble constant, and the model falls 9% short. Here is the uncomfortable part. Both sides have strong reasons to trust their method. The early universe team starts with the Planck satellite's exquisitely precise map of the cosmic microwave background. Their analysis is purely mathematical. They plug numbers into equations, and out comes a prediction. No complicated measurement chain, no worrying about star crowding or dust. Their result carries enormous statistical confidence. The nearby galaxy team builds their measurement from the ground up, step by careful step. Parallax distances anchor the Cepheid calibration. The Cepheids calibrate the supernovae. The supernovae measure the expansion. Each rung of the ladder has been checked multiple times by multiple teams using different instruments. For years, physicists hoped that checking the ladder one more time with a better telescope would reveal a hidden mistake. A slightly miscalibrated star. A dust cloud distorting the light. Anything. Instead, the checks kept confirming the ladder. The gap stayed at 9%. When both methods are verified and still disagree, the only remaining explanation is that something physical is causing the discrepancy. Something in the universe itself is behaving differently than the standard model predicts. And that means new physics, unknown forces, undiscovered particles, rules that nobody has written yet. An entirely new chapter of human understanding may need to be written. And the story of how scientists finally confirmed that the problem was real after decades of debate centers on a single telescope and the data it returned from 130 million light years away. Stars inside a galaxy do not sit alone in empty space with comfortable distances between them. Near the center of a galaxy, they pack together so densely that if you stood on a planet in one of those regions, the night sky would never go dark. Stars would fill the view in every direction, layered on top of each other, blending into a continuous smear of light. This creates a serious problem when you are trying to measure a Cepheid variable star inside a distant galaxy. As Cepheid pulses, it brightens and dims on a precise schedule. You watch it over days or weeks, track the rhythm, calculate the true brightness, and compare that to how bright it appears from Earth. The comparison gives you the distance. But what if other stars are overlapping with the Cepheid in your image? Their light bleeds into the same tiny patch of your camera sensor. The Cepheid appears brighter than it actually is because you are measuring the Cepheid plus the glow of its neighbors. A star that appears too bright looks closer than it really is. Pull that error through the entire measurement chain and your final expansion rate comes out too fast. This is the crowding problem, and it is not hypothetical. In dense regions of galaxies, multiple stars can blend into a single bright spot in a telescope image. Astronomers develop software to try and subtract the background glow of neighboring stars, but subtraction is not the same as actually seeing the stars separately. It is an estimate, and estimates carry uncertainty. The Hubble Space Telescope launched in 1990, and despite a famous early problem with its mirror that was later corrected, it became the most productive scientific instrument in history. But its primary mirror measures just over 7.5 feet across. For a telescope in space, that is impressive. For resolving individual stars inside a galaxy 60 million light years away, it sits right at the edge of what is physically possible. Critics of the Rias expansion measurement argued that crowding was inflating the apparent brightness of Cepheids in precisely the way that would push the measured expansion rate upward. The effect would be subtle, small enough to survive initial checks, but large enough applied across hundreds of Cepheid measurements to produce a systematic bias in the final answer. This was a legitimate scientific concern. Rias and his team had done extensive work to account for crowding. They developed sophisticated models, tested their corrections, and published detailed analyses. But critics pointed out that if the correction method itself had a flaw, no amount of testing would reveal it. The debate had reached a wall. Words and models and corrections could not settle it. Only an image could. An image sharp enough to separate a Cepheid from every star around it, so clearly that crowding became irrelevant. An image from a telescope so powerful that the question of whether neighboring starlight was contaminating the measurement simply disappeared. The James Webb Space Telescope was designed to deliver exactly that. And when its first Cepheid data came back, both sides of the debate held their breath. Science runs on skepticism. When two measurements disagree, the first instinct is always to look for the mistake. That is how science is supposed to work. Extraordinary claims require extraordinary evidence. A crack in the foundation of cosmology qualifies as an extraordinary claim. So when the Hubble tension emerged in the late 2000s and grew sharper through the 2010s, the dominant response from most of the physics community was measured doubt. The early universe measurement from the Planck satellite was precise, elegant, and grounded in equations that had passed every other test. The nearby galaxy measurement from Rias and his team involved a long chain of steps, each with its own source of potential error. The logic was straightforward. A long chain is more likely to break than a short one. The distance ladder requires calibrating Cepheids using parallax, then using those Cepheids to calibrate supernovae, then using supernovae to measure expansion. 3 rungs, 3 places where a subtle, systematic error could creep in and compound. Crowding was the prime suspect, but it was not the only one. Space contains vast clouds of gas and dust. Dust scatters light, making objects look redder and dimmer than they really are. Astronomers correct for dust using known relationships between dust content and its effect on different wavelengths of light, but those corrections are themselves calibrated from models. If the dust models were slightly off, the Cepheid brightness measurements would be slightly off. There was also the question of metallicity. Cepheid stars and galaxies with different chemical compositions might not follow the exact same period luminosity relationship that Henrietta Leavitt discovered. If the pulsing rhythm tells a slightly different story depending on the star's chemistry, then using a single calibration for all Cepheids would introduce a bias. Each of these concerns was real. Each had been studied. Reus and his collaborators published response after response, addressing every systematic error that critics raised. Their corrections held up. Their numbers stayed high. Still, the community waited. The James Webb Space Telescope had been in development since the 1990s. It launched on Christmas Day in 2021, after years of delays and cost overruns that tested everyone's patience. Its mirror spans over 21 feet, nearly 3 times the diameter of the Hubble Space Telescope. It operates in infrared light, which passes through dust clouds far more easily than visible light. Every specification it carried was designed to push past the limitations that critics blamed for the Hubble tension. If crowding was inflating the nearby galaxy expansion rate, Webb would see it immediately. Individual stars that Hubble smeared into one bright blob would appear as clearly separate objects under Webb's gaze. The Cepheid brightnesses would drop, the distances would stretch, the expansion rate would slide down toward the Planck prediction. That was the hope of roughly half the cosmology community. Webb launched. Webb reached its orbit, Webb began collecting data, and then something happened that nobody on the skeptical side of the debate wanted to see. The James Webb Space Telescope is not a slightly better version of the Hubble Space Telescope. It is a fundamentally different machine, built to answer questions that Hubble never could. To understand the difference, picture Hubble as a sharp-eyed hawk watching from a rooftop. Webb is a hawk the size of a tennis court, hovering 1 million miles from Earth in the cold dark, wearing vision that can see entirely different colors of light, and chilled to temperatures that make liquid nitrogen feel warm. Webb's primary mirror is made of 18 hexagonal gold-coated panels that folded up for launch and unfolded in space like an origami sculpture in reverse. Stretched from tip to tip, the mirror spans over 21 feet. When Hubble's 7.5-foot mirror was state-of-the-art, the idea of getting 21 feet of precision optics into space was a fantasy. The gold coating is intentional. Webb sees the universe in infrared light, the kind your TV remote uses to talk to your television. Stars emit infrared. Galaxies emit infrared. But more critically, infrared light passes through dust clouds that block visible light completely. When Hubble tried to peer into a dusty galaxy and find Cepheid stars, the dust scattered visible light and blurred the view. Webb sees straight through the same dust clouds as if they are not there. Webb sits at a location called the second Lagrange point, about 1 million miles from Earth on the opposite side from the Sun. At that location, the gravitational pull of the Sun and Earth balance in a way that lets Webb orbit the Sun at the same rate Earth does, staying fixed in relation to our planet without burning fuel constantly. 1 million miles of separation also means Webb is far enough from Earth's heat that space itself keeps it cold. And cold matters enormously. Webb's infrared sensors need to operate at temperatures close to negative 448 degrees Fahrenheit, just a few degrees above absolute zero. At that temperature, the sensors stop generating their own infrared glow that would contaminate readings. A special sun shield the size of a tennis court, layered like a giant umbrella, blocks sunlight and keeps the instrument side of the telescope in permanent shadow. The result is a telescope that can see individual stars in galaxies tens of millions of light years away with clarity that simply could not exist before. When Webb looked at a galaxy that Hubble had studied and found a blurry cluster of overlapping stars, Webb resolved it into dozens of separate, distinct points of light. Cepheid variables that Hubble could barely distinguish from their neighbors appeared to Webb as clean, isolated signals against a dark background. This was the instrument the Hubble tension debate had been waiting for. Both sides agreed. Whatever Webb found would be decisive. Either crowding would show up in the data as a real problem, proving the nearby galaxy measurement was biased too high, or crowding would disappear, proving the Rias result was accurate and the tension was real. The answer came faster than anyone expected. Adam Rees and his team loaded Webb with a specific mission. They wanted to observe Cepheid variable stars in galaxies that Hubble had already studied. By looking at the same stars with a far more powerful instrument, they could directly test whether crowding had been inflating the Hubble measurements. They chose galaxies spread across a range of distances out to roughly 130 million light-years away. 130 million light-years means the light Webb captured left those galaxies 130 million years ago, before the dinosaurs went extinct on Earth. That light traveled across an almost incomprehensible distance and arrived at Webb's mirror with enough precision to identify individual pulsing stars. Webb began returning data in 2023. Rees's team compared the new Webb images to the old Hubble images side by side. In the Hubble images, Cepheid variables appeared as bright patches inside dense star fields. The software corrections that subtracted neighboring starlight had been doing the best possible job, but the neighboring stars were still there in the image, blending slightly. In the Webb images, the same regions of sky look completely different. Stars that Hubble had seen as a single bright blob appeared to Webb as multiple separate points of light. The Cepheids stood out clearly. Their neighboring stars were distinct objects sitting beside them, not bleeding into them. Crowding as a source of measurement error was eliminated not by correction or subtraction, but by seeing clearly enough that it simply stopped being a problem. The team then measured the brightness of the Cepheids in the Webb data directly, without relying on crowding corrections. The results matched the Hubble measurements. The Cepheids were exactly as bright as Hubble had calculated, even without the corrections. The crowding concern had been eliminated as a significant factor. The Hubble measurements were accurate. In 2024, Rees published the formal results. The paper concluded that the local expansion rate of the universe, measured through Cepheids and supernovae using Webb's clean data, remained at roughly 46 miles per second per megaparsec. The number had not moved. Every major source of error that critics had proposed turned out to be small enough that it could not close the gap. The Hubble tension was real. A measurement problem could not explain it. This placed the entire burden of explanation onto physics itself. The universe is expanding faster than the standard model predicts. That model is built on decades of careful science, tested against almost every type of observation astronomers have made. And in one specific precise measurement, it is wrong. Something is causing the universe to move faster than it should, something the standard model does not include. And at almost the same moment that Rees was publishing his confirmation, another scientist was introducing a new measurement that made the picture stranger still. The press conference was quiet by the standards of scientific announcements. Adam Rees did not shout. He did not pound a podium. He spoke carefully, in the measured way that physicists speak when they are describing something that makes them genuinely uncomfortable. He said that, with the James Webb Space Telescope confirming his measurements, measurement error could no longer explain the Hubble tension. He said the only remaining possibility was that the universe did not operate the way the standard model described. He said, in plain language that anyone could understand, that we may have misunderstood the universe. For a Nobel Prize winner to say that publicly is not a small thing. Scientists are trained to be cautious. They hedge. They say data suggest and results are consistent with. When a physicist who has spent 3 decades measuring the universe with the best tools available, and who has the Nobel Prize as evidence that those measurements matter, says plainly that the universe may be operating by rules we have not discovered, the scientific community listens differently. Rees has been careful about what he claims. He does not say he knows what is wrong with the standard model. He says something is wrong. The distinction is important. Physics does not yet have a candidate explanation that everyone agrees on. Several theories exist. None of them are proven. All of them require either new particles, new forces, or new modifications to Einstein's equations. What Rius did confirm is that the problem is real and will not be solved by checking the measurement chain one more time. Every systematic error that could plausibly explain the Hubble tension has now been examined. Crowding, dust, metallicity, variations in Cepheid stars, calibration choices for supernovae, all of them have been tested. None of them are large enough to close a 9% gap. This confirmation changes the nature of the debate. Before Webb, the Hubble tension was a problem that might go away, a nagging discrepancy that future data might resolve. After Webb, it is a fixed fact. The universe, measured locally, expands roughly 9% faster than the standard model predicts from early universe observations. Rees described the situation with an analogy. Imagine building a detailed model of a bridge using the laws of engineering. Your model predicts the bridge will flex by 1 inch under load. You go measure the actual bridge. It flexes by 1.1 inches every single time with every measuring tool you own, no matter who does the measuring. At some point, you stop blaming the measuring tape and start suspecting your model of the bridge is missing something. The standard model of cosmology built a prediction. The universe is returning a different measurement. Every measuring tape has been checked. The model is missing something. And while Rius's team was working through this conclusion, a completely different team was measuring the same expansion with completely different stars. Their result added a layer of confusion that nobody fully expected. Wendy Friedman has been measuring the expansion of the universe for most of her career. She leads the Chicago Carnegie Hubble program, and her work sits at the center of the Hubble tension debate from a different angle than Rius. While Rius built his measurement on Cepheid variable stars, Friedman and her team placed their trust in a different category of stellar rulers: red giant stars. When a star roughly the size of our sun exhausts the hydrogen fuel in its core, it enters a phase called the red giant stage. The outer layers swell outward enormously, sometimes to hundreds of times the star's original size. The star brightens dramatically during this phase, and then, at a specific moment in that process, the star reaches a precise maximum brightness before it dims again. That peak brightness is consistent across all red giant stars of a certain type. It occurs at a specific point in the star's internal physics, tied to helium ignition in the core, which happens at almost exactly the same conditions regardless of where the star is or what galaxy it lives in. This makes red giant stars useful as standard candles, objects with a known true brightness you can use to measure distance. Friedman's team pointed the James Webb Space Telescope at several galaxies and used these red giant stars to measure how far away those galaxies were. No Cepheids, no Type Ia supernovae as the primary anchor, a completely independent route up the distance ladder using a different stellar population that does not suffer from the crowding problem that Cepheids face. Her team published their results in 2024. The answer they got was 43.4 miles per second per megaparsec. Not 42, which is the Planck prediction from the early universe, and not 46, which is the Rius measurement from Cepheids and supernovae, 43.4. Sitting in the middle, this created an immediate and complicated reaction in the scientific community. One interpretation, Friedman's result, suggests the Hubble tension might be smaller than Rius measured. If the true expansion rate is closer to 43 than 46, the gap between the local universe and the early universe prediction shrinks. Maybe the standard model does not need as drastic a fix as Ries's numbers implied. Another interpretation, a third independent measurement producing a third different number, means the problem is actually larger than it appeared. Now the question is not just why the local measurement and the early universe prediction disagree. The question is why Cepheids and red giants, two independent methods applied to the same universe, also disagree with each other. Ries's team and Friedman's team are now in active disagreement about which stellar ruler is more reliable. Both believe their method is correct. Both have data from the James Webb Space Telescope, both are applying careful calibrations, and both get different answers. The Hubble tension started as one problem. Friedman's measurement may have turned it into two problems, stacked on top of each other. And the deeper physics gets into this question, the more the theoretical explanations start to look like science stretching to its absolute limit. Friedman's team did not stop with red giant stars. They added a second independent stellar ruler that has rarely been used in cosmology at this scale: carbon stars. These are stars in the final stages of their lives, puffed out and cool, with surfaces rich in carbon atoms that have been dredged up from the star's core. Carbon stars glow in a way that is distinct from most other stars. Their spectra, the pattern of light frequencies they emit, carry a recognizable chemical signature. And crucially, carbon stars in a certain phase of their evolution cluster tightly around a consistent brightness level. Think of it like a specific model of car. Different individual cars of the same model will have slightly different paint jobs or minor variations, but they all have the same engine producing roughly the same horsepower. Carbon stars in this phase are similar. Individual variation exists, but the average brightness lands reliably in a narrow range. That predictability makes them useful for measuring distance. Friedman's team used carbon stars as a cross-check against their red giant measurements. Both methods pointed to similar distances for the same galaxies. When two completely different types of stars using different physics give you the same answer, that is a strong signal you are measuring something real. Now, here is where the debate sharpens. Rees's team uses Cepheid variables as their primary ruler. Friedman's team argues that Cepheids carry systematic errors that are difficult to remove. Cepheids live in the disk of a galaxy, the flat, actively star-forming region where dust is thick and crowding is worst. Red giants and carbon stars are older stars. They tend to live in the halo or outer regions of a galaxy, where dust is thinner and crowding is minimal. Measuring them requires fewer corrections. Rees disagrees. His team argues that the Cepheid calibration has been tested more thoroughly than any other method in the field, across decades of observations, checked against multiple independent anchors, including geometric distances, to nearby galaxies. The Webb data, he argues, confirmed those calibrations are sound. The argument is technical, but the stakes are simple. If Cepheids have an undetected systematic error, Ries's expansion rate is too high. The Hubble tension shrinks. The standard model needs a smaller fix. If red giants or carbon stars have an undetected error, Friedman's middle ground rate is too low. The Hubble tension is as large as Ries measured. The standard model needs a much bigger fix. Both cannot be right. The universe has one true expansion rate. The measurements will eventually converge on it. What scientists do agree on is this: the standard model's prediction of 42 miles per second per megaparsec looks increasingly hard to defend. Even Friedman's lowest estimate, 43.4, sits above the Planck number. Every current local measurement, whether from Cepheids, red giants, or carbon stars, lands above the early universe prediction. The gap between the early universe and the local universe is almost certainly real. What caused it, and how large it truly is, depends on which stellar ruler you trust. And beyond the question of which ruler is right, lies an even deeper question. What physical process could have pushed the universe to expand faster than all of our models say it should? The answer might require us to rewrite the rules of physics entirely. 43.4 miles per second per megaparsec. On the surface, this number sounds like progress. If the Planck satellite predicts 42 and Rias measures 46, then Friedman landing at 43.4 feels like the two sides are getting closer, like the truth is somewhere in the middle, and science is slowly converging on it. The reality is more uncomfortable than that. Start with what the number actually means for the Hubble tension. The tension exists because the early universe measurement and the local measurement disagree. If Friedman is right, the gap shrinks from 9% to about 3%. 3% sounds manageable. In cosmology, 3% is still a problem without a solution. Even at 43.4, the universe is expanding faster than the standard model says it should. Even at 43.4, physicists still need to explain what is driving that extra speed. The standard model has no built-in mechanism for making the local universe faster than the ancient light predicts. So the core problem survives, just slightly smaller. But the bigger issue is what Friedman's number does to the broader picture. Before her results, the debate was two numbers against each other. Now it is 3. Cepheids say 46, red giants and carbon stars say 43.4, the cosmic microwave background says 42. 3 methods, 3 answers, each backed by serious scientists with serious data. In science, when independent methods measuring the same quantity give different answers, the first question is always, which method has the hidden flaw? But here, all 3 methods have been scrutinized heavily, and none of them collapse under examination. The Cepheid calibration has survived decades of checks, and now a Webb confirmation. The red giant peak brightness has solid theoretical grounding. The Planck data is the most precise map of the early universe ever made. 3 apparently sound methods. 3 different numbers. The universe is telling scientists something, but it is not yet clear what. There is a version of events where Friedman's measurement is exactly right, and the answer truly is 43.4. In that scenario, both Rees and the Planck team are slightly wrong, for different and unrelated reasons, and the universe happens to expand at a rate that neither camp's primary measurement captured perfectly. This is possible. Physics has surprised scientists before. But for this to be true, 2 independent systematic errors would need to have pushed 2 unrelated methods in opposite directions by almost exactly the right amounts to bracket the true value. That kind of coincidence makes most physicists uncomfortable. The debate has sharpened into a question that no amount of additional calibration seems able to answer cleanly. Is the Hubble tension a 9% problem, a 3% problem, or something in between? And regardless of which number wins, the mystery of what is causing any gap at all remains completely open. Friedman's result did one thing that everyone agrees on. It proved the problem is harder than it looks. The universe does not seem to care that scientists have given it 3 different rulers to measure itself with. It keeps returning numbers that disagree, and somewhere in that disagreement, a piece of physics is hiding. If the universe is expanding faster than the standard model predicts, something must have given it extra speed. The most popular theoretical explanation for that extra speed is called early dark energy. Understanding it requires stepping back to the first moments after the Big Bang. The Big Bang was not an explosion in space. Space itself expanded from a single point. In the first tiny fraction of a second, the universe went from impossibly small to the size of a grapefruit. Then it kept expanding, but more slowly. Gravity pulled matter together. Radiation filled the hot, dense chaos. Everything was in a fierce balance between expansion and the forces trying to slow it down. The standard model assumes that balance was governed by known physics the whole way through. Dark energy, the force pushing everything apart today, was present from the beginning but played a modest role in the early universe. Gravity and radiation dominated. The model predicts how fast the universe should have expanded through those early stages, and from that, it calculates what the expansion rate should be today. Early dark energy is a theory that challenges one piece of that picture. It proposes that dark energy was much stronger in the early universe than the standard model assumes. In this scenario, before the universe was a few 100,000 years old, there was an extra burst of outward pressure pushing space apart faster than expected. Then, after that brief phase ended, early dark energy faded away, and the universe continued expanding under the dark energy we observe today. If this happened, the ruler that scientists use to calculate the current expansion rate would be calibrated slightly wrong. The universe spent its early years expanding faster than the standard model accounts for. When scientists measure the cosmic microwave background and use it to predict the current expansion rate, they are unknowingly plugging in a slightly too slow history. The prediction comes out too low. The local measurement comes out higher. The gap looks like a mystery when it is actually evidence of that early burst. This theory is attractive because it leaves the rest of the standard model mostly intact. No need to modify Einstein's equations. No need to invent entirely new particles. just a modification to the behavior of dark energy at very early times, and the gap between 42 and 46 could narrow significantly. The problem is that early dark energy is a theory built to fit the data. Physicists have not detected it directly. No telescope has seen its signature. Models of early dark energy make specific predictions about the patterns in the cosmic microwave background, and so far those patterns are not showing up clearly in the data. It is a solution that works mathematically, but has not yet shown its face in an observation. Whether it is real, a placeholder, or a dead end entirely depends on data that future instruments have not yet gathered. But early dark energy is only one idea. Other physicists went in a completely different direction. Dark matter is one of the most confirmed mysteries in physics. Scientists have never seen it directly. No telescope has ever captured its light because it produces none. No detector has ever caught a particle of it. And yet the evidence that dark matter exists is overwhelming. Galaxies rotate in a way that makes no sense without extra mass. Light bends around clusters of galaxies far more than the visible matter inside those clusters could cause. The large-scale structure of the universe, the way galaxies cluster into filaments and walls across billions of light years, matches computer models only when dark matter is included. Something massive and invisible fills the universe, and it holds everything together. The standard model treats dark matter as cold, slow-moving particles that interact with ordinary matter only through gravity. They do not absorb light. They do not emit light. They do not bounce off each other or off regular atoms. They just pull slowly over vast distances, shaping the universe through gravity alone. This assumption of isolation may be wrong. Some physicists now theorize that dark matter particles interact with photons, which are particles of light, in a subtle way that ordinary dark matter models ignore. If dark matter and photons exchange even tiny amounts of energy, the pressure inside the early universe would shift slightly. That shifted pressure would alter how fast matter clumped together in the early cosmos. And that altered clumping would change the prediction for the expansion rate that scientists read from the cosmic microwave background. In plain terms, if dark matter is slightly sociable instead of perfectly isolated, the early universe measurement could be off. The standard model assumes perfectly isolated dark matter. If dark matter is actually interacting, the model's prediction is built on a false assumption. This theory goes by the name interacting dark matter. It is one of several variations on the dark matter concept that physicists are actively investigating. Some versions propose that dark matter interacts with neutrinos, the tiny, near-massless particles that flood through you at millions per second without touching anything. Some versions propose dark matter interacts with itself, creating dark atoms and dark chemistry invisible to any instrument we currently have. None of these are proven. All of them remain in the category of theory, not confirmed science. But each one carries a serious implication. If dark matter behaves differently than assumed, then every calculation that used the old assumption is slightly wrong. The timeline of how the universe evolved, the predicted patterns in ancient light, and the expected current expansion rate would all shift by small but significant amounts. And in cosmology, small amounts matter enormously. The numbers in these equations need to be right across billions of light years and billions of years of time. A tiny error in a fundamental assumption compounds into a large disagreement between prediction and observation. Dark matter has been mysterious since its discovery. The Hubble tension may be revealing a new layer of that mystery, one that has been hiding in plain sight inside every cosmological calculation ever made. Every explanation discussed so far assumes that the standard model is roughly correct and that some missing piece of physics needs to be added to fix the discrepancy. Early dark energy adds something to the early universe. Interacting dark matter changes a property of something already in the model. Both of these approaches work within the existing framework and try to patch it. The cosmic void theory takes a different approach entirely. It says the universe is fine, the standard model is mostly right. The problem is where we are standing. On the largest scales, the universe is remarkably uniform. Matter is spread across billions of light years in a mostly smooth distribution. But on smaller scales, matter clusters into giant structures, galaxy filaments, galaxy walls, galaxy clusters, and between them, enormous empty regions called cosmic voids. These voids are not perfectly empty. They contain some galaxies, but compared to the dense filaments and walls around them, they are dramatically underdense. Our galaxy, the Milky Way, sits in a region that some astronomers believe is less dense than the cosmic average. If that is true, we may be living inside a void, a bubble of underdense space, surrounded by denser walls of matter farther out. Here is why that matters for the Hubble tension. Inside a void, the gravitational pull from surrounding matter is not balanced equally from all sides. The dense walls of galaxies further out pull our region of space toward them. This would cause galaxies in our local neighborhood to flow outward toward those dense walls, adding to their apparent recession speed. When astronomers measure how fast nearby galaxies are moving away, they would be measuring a combination of the true cosmic expansion rate and this local outward flow. The result would be a locally measured expansion rate that appears faster than the true rate. The discrepancy between local measurements and the early universe prediction could be partially or fully explained by our unusual position inside this void. The void theory is appealing because it requires no new physics, no new particles, no modification to Einstein's equations. The universe runs on the same rules it always has. We are just in a peculiar neighborhood. The problem is the numbers. Astronomers have mapped our cosmic neighborhood carefully and found evidence of a local underdensity sometimes called the local hole. Some estimates suggest this void is roughly 1 billion light-years wide. That is enormous. Whether a void of that size could generate enough outward flow to explain the full 9% discrepancy is an active debate, and current estimates suggest it probably cannot account for all of it. A partial explanation that requires no new physics is still something worth taking seriously. The void effect may be one ingredient in a larger recipe combining with another physical cause to produce the full Hubble tension. But the void theory has one other uncomfortable implication. If we are inside a special region of the universe, we may be getting a systematically biased view of everything around us. Every local measurement we make could be slightly warped by our position. The universe might look different from somewhere else entirely. The standard model of cosmology, formerly called the lambda cold dark matter model, is the most successful description of the universe ever built. It correctly predicts the distribution of galaxies across billions of light years. It matches the precise pattern of temperature variations in the cosmic microwave background. It explains the abundance of hydrogen and helium formed in the first minutes after the Big Bang. Across test after test, it holds. The Hubble tension is not the first crack, but it is the deepest one. There are others. Astronomers studying the large-scale structure of the universe have found that the actual clustering of galaxies is slightly less pronounced than the standard model predicts. This discrepancy has a technical name, the sigma-8 tension. It is a separate problem from the Hubble tension, but it points to the same uncomfortable conclusion. In two independent measurements of two independent properties of the universe, the standard model's predictions fall short. Sigma-8 and the Hubble tension are connected through the physics of dark matter and dark energy. Both tensions suggest that either the early universe physics was slightly different from what the model assumes, or the properties of dark matter or dark energy are slightly different from what the model builds in. Then there is the question of the cosmological constant. The cosmological constant is the term in Einstein's equations that represents dark energy. It assumes dark energy is perfectly uniform across all of space and perfectly constant through all of time, a fixed, unchanging background pressure pushing the universe apart. Some observations suggest dark energy might not be constant. Recent data from a survey called the Dark Energy Spectroscopic Instrument hints that dark energy may have changed strength over the history of the universe. If dark energy evolves over time, the cosmological constant needs to be replaced with a more complex description. The standard model would need to be rebuilt around a dark energy that behaves rather than simply existing as a fixed background number. None of these cracks individually collapse the standard model. Each has an uncertainty range that leaves room for the model to survive. But the pattern of the cracks is significant. They are not random, they cluster around the same part of the model: the assumptions about what dark energy and dark matter actually do. The model was built in an era when astronomers could detect the effects of dark matter and dark energy, but had almost no ability to study their properties in detail. It assumed the simplest possible behavior for both. Dark matter moves slowly and does not interact. Dark energy sits constant and unchanging. Those simplest assumptions produced a model that matched the data available at the time spectacularly well. The problem is that the data available today is far more detailed, and the cracks are appearing exactly where the simplest assumptions were made. Physics has a long history of simple assumptions that held until the instruments got good enough to challenge them. Albert Einstein published his theory of general relativity in 1915. It described gravity in a completely new way. Before Einstein, gravity was a force that objects exerted on each other across space. After Einstein, gravity was the bending of space and time itself, caused by the presence of mass and energy. A massive object curves the fabric of space-time around it, and other objects follow those curves the way a ball rolls down a hill. General relativity has passed every test thrown at it for over 100 years. Mercury's orbit around the sun matched its predictions precisely. Light bending around the sun during a solar eclipse matched its predictions in 1919. Gravitational waves from colliding black holes, detected for the first time in 2015, matched its predictions exactly. GPS satellites require corrections based on general relativity to work accurately. The equations are right, but right on every tested scale does not mean right on every scale. General relativity has been tested on human scales, solar system scales, and scales up to a few thousand light years. When applied to the entire observable universe, spanning 46 billion light years, Einstein's equations make assumptions that may not hold. The standard model of cosmology is built on general relativity, applied at cosmic scales. If the equations behave differently than expected at those enormous scales, the model built on them would be wrong, in ways that show up as exactly the kind of discrepancies astronomers are seeing. Several modified gravity theories propose small changes to Einstein's equations that become significant only at cosmic distances. One family of theories adds extra terms to the equations that kick in at very low gravitational strengths, the kind found across vast stretches of nearly empty space between galaxies. These modifications leave solar system physics completely unchanged, keeping all of general relativity's successful predictions intact, while altering the behavior of gravity on scales of hundreds of millions of light years. If gravity behaves differently at cosmic scales, the way galaxies cluster, the way dark matter structures grow, and the predicted expansion rate of the universe could all shift in ways that might close the Hubble tension. This is a profound idea. Einstein's equations were derived from physical principles, tested against observations, and refined over a century. Proposing that they need modification is not a small claim. It requires extraordinary evidence, not just the Hubble tension alone. Most physicists treat modified gravity theories as a last resort. If early dark energy, interacting dark matter, and local void effects all fail to explain the tension, modified gravity enters the conversation more seriously. Currently, it sits in the background, a theoretical possibility kept alive by the fact that every other explanation is also unproven. Einstein himself modified his equations multiple times. He introduced the cosmological constant, removed it, and was vindicated decades later when dark energy proved it should have stayed. The history of physics is full of equations that turned out to be correct within a range and approximate outside of it. General relativity may be the next equation in that long line. The age of the universe sits at 13.8 billion years. This number appears in textbooks, on museum walls, in every astronomy documentary made in the past decade. It is one of the most precisely calculated numbers in science. It is also directly tied to the Hubble constant. And if the Hubble constant is wrong, the age is wrong too. Here is the basic logic. The universe is expanding. If you run that expansion backward, like rewinding a video, everything eventually converges back to a single starting point. The faster the universe is expanding, the less time it took to reach its current size. A faster expansion means a younger universe. The Planck satellite's prediction of 42 miles per second per megaparsec leads to an age of about 13.8 billion years. If the true expansion rate is closer to 46, the universe is younger by more than a billion years. The corrected age would fall somewhere around 12.5 to 13 billion years. A billion years sounds abstract. Consider what that billion years is supposed to contain. The oldest stars astronomers have found are roughly 13.2 billion years old. They formed not long after the universe began. If the universe is only 12.5 billion years old, those ancient stars would be older than the universe itself. That is physically impossible. A star cannot predate the universe it lives in. This age paradox would be a serious problem if the faster expansion rate wins. It would mean one of three things. Either the dating of ancient stars contains an error, or the expansion rate measurement contains an error, or the universe underwent some phase early in its history that stretched time in ways the standard models do not account for. Some physicists point to this tension as evidence against the faster local expansion rate. If accepting Rias's measurement leads to stars older than the universe, perhaps the measurement chain still contains a systematic error too subtle for Webb to catch. Others argue that stellar age dating also carries its own uncertainties, and that both the stellar ages and the expansion rate need to be refined before drawing firm conclusions. The age paradox does not prove anyone wrong. It shows how deeply connected every measurement in cosmology is to every other. Change one number, and ripples spread through every calculation in the field. 13.8 billion years feels like settled science. Right now, it is a number under genuine pressure. The Hubble constant determines the universe's past. It also determines its future. And the future, implied by different expansion rates, looks very different depending on which number you trust. The fate of the universe has three classical possibilities. In the first, the universe expands, gravity gradually wins, and everything eventually falls back together in a collapse sometimes called the Big Crunch. In the second, expansion and gravity are perfectly balanced, and the universe expands forever at a decreasing rate that approaches but never quite reaches zero. In the third, expansion wins permanently and galaxies drift apart forever. The discovery of dark energy in 1998 eliminated the first option. The universe is not just expanding, but accelerating. Gravity is losing. The third option, permanent expansion, is now the overwhelming scientific consensus for the universe's long-term fate. But the details of that expansion matter enormously. How fast is the universe accelerating? Is dark energy getting stronger over time, staying constant, or weakening? If the faster expansion rate of 46 miles per second per megaparsec reflects a dark energy that is growing stronger over time, the ultimate fate of the universe becomes more extreme than simply drifting apart. An accelerating acceleration would eventually shred everything. Galaxies would be torn apart. Then solar systems, then planets, then individual molecules, then atoms, then the particles inside atoms. Physicists call this the Big Rip. If dark energy is constant, the universe expands, but structures are not torn apart. Gravity holds galaxies, solar systems, and planets together even as the space between them stretches. Stars would eventually burn out. The universe would grow cold and dark, but it would not tear itself apart. The difference between those two futures hinges on properties of dark energy that scientists cannot yet measure precisely enough to determine. The Hubble tension is directly connected to this question because the expansion rate feeds into the equations describing dark energy's strength and behavior over time. A 9% error in the expansion rate produces a measurable error in dark energy predictions. Whether the universe ends in a long, cold darkness or a violent cosmic shredding is still an open question, and the Hubble tension sits directly at its center. The universe has a fate. We do not yet know which one. Imagine the universe as a fabric being pulled from opposite ends. Dark energy pulls outward, gravity pulls inward. Right now, on small scales, gravity wins. Planets orbit stars, stars cluster into galaxies, galaxies group into clusters. The fabric holds, but on the larger scales, dark energy is winning. The space between galaxy clusters is growing, carrying them apart faster than gravity can compensate. If dark energy grows stronger over time, that balance tips further toward dark energy in every direction. The ripping begins at the largest scales first. Roughly 20 billion years from now, according to some theoretical models, galaxy clusters would begin to disintegrate. The dark energy pressure would overwhelm the gravity holding clusters together. Galaxies would scatter apart from one another, drifting into isolation. Closer to the rip itself, individual galaxies would lose their structure. Stars that have orbited galactic centers for billions of years would find themselves pulled outward as the dark energy pressure penetrated inward. The Milky Way would dissolve. About 2 months before the end, solar systems would come apart. Earth's orbit around the sun would expand and break. Planets would drift free. Minutes before the end, planets themselves would be torn apart. The force pulling on one side of a planet would exceed the force pulling on the other side by enough to overcome the structural strength of rock. In the final seconds, individual atoms would be ripped apart. The electrons orbiting atomic nuclei would be stripped away by the differential dark energy pressure. The nuclei themselves would dissolve as the strong nuclear force, one of the most powerful forces in nature, was overwhelmed by dark energy at subatomic scales. The Big Rip is speculative. It requires dark energy to be growing in strength over time, which is a property scientists have not confirmed. Current observations are consistent with constant dark energy, and constant dark energy leads to the long, cold darkness instead of the rip. But dark energy is not understood well enough to rule out growth. The Hubble tension points to something unexpected happening with the expansion of the universe. If that something is a dark energy that is more dynamic than assumed, the Big Rip moves from a theoretical curiosity to a genuine possibility. The universe may already be on a path toward tearing itself apart. The answer lies in measurements not yet precise enough to make. Here is something that should genuinely unsettle you. The universe is expanding. The farther away a galaxy is, the faster the space between it and us grows. At a great enough distance, the space between us and another galaxy grows faster than light can cross it. Light leaving that galaxy today will never reach us. It is running on a treadmill, moving faster than it can run. This boundary, the distance at which recession speed equals the speed of light, is called the cosmic horizon. Anything beyond it is permanently invisible to us. We cannot receive any signal from it. We cannot send any signal to it. It is cut off from our observable universe as completely as if it existed in a different reality. And that boundary is not fixed. As dark energy accelerates the expansion, the cosmic horizon shrinks inward. Galaxies that are currently visible, sitting just inside the boundary, are being carried past it over billions of years. Their light, already traveling toward us, will still arrive, but new light leaving those galaxies right now will never make it. From our perspective, those galaxies appear to slow down and redden as their light gets stretched by the expanding space. Eventually, they fade below the limit of any instrument's ability to detect them. They do not disappear explosively. They simply dim, redden, and vanish, leaving no trace in the sky except the light that left before the boundary swallowed them. Astronomers estimate that roughly 100 billion galaxies currently exist within our observable universe. Over the next few trillion years, the vast majority of those galaxies will cross beyond our horizon. The night sky of the distant future would show a tiny fraction of what we can see today. Civilizations arising in that far future universe would look out at the night sky and see only the galaxies gravitationally bound to our local group, a small cluster of dozens of galaxies. The immensity of the universe, the hundreds of billions of galaxies beyond our local group, would be completely invisible to them. They might conclude from their observations that the universe contains only a handful of galaxies. We happen to live in an era where the full extent of the universe is still visible. The evidence of its true scale still reaches us. That window is closing, one galaxy at a time, right now. The Hubble tension determines how fast that window closes. A faster expansion rate accelerates the disappearance. The universe's inventory is being hidden from future observers, And we are watching the last age in which the full picture is available. When equations built on known physics fail to match observations, physicists have two choices: fix the equations, which means modifying existing theories, or add something to the equations, which means discovering new physics. The Hubble tension currently resists fixing. Every known particle, every known force, every known modification to the standard model has been tested against the discrepancy. None of them close the gap completely without creating other problems elsewhere. That leaves the second option: something new needs to be discovered. Early dark energy, discussed earlier, is one candidate for new physics. But physicists have gone further. Some propose an entirely new particle called a sterile neutrino. Ordinary neutrinos are nearly massless particles that interact almost nothing with ordinary matter. They pass through the entire Earth as if it is not there. A sterile neutrino would be even more isolated, interacting through gravity alone. Adding a population of sterile neutrinos to the early universe could alter the expansion history in ways that shift the predicted current expansion rate upward. Others propose a new light particle, sometimes called dark radiation. In the early universe, radiation pressure competing with gravity shaped how fast matter clumped together and how fast the universe expanded. Adding a new type of radiation, one that interacts only weakly with known particles, would add pressure to the early universe and shift the expansion prediction. Some theoretical physicists have gone further still, proposing phase transitions in the early universe. A phase transition is when a substance changes state abruptly, water freezing into ice, or steam condensing into liquid. The universe itself may have undergone phase transitions in its early moments, brief periods where the energy content of space changed abruptly. A phase transition near the time of the cosmic microwave background could have altered the expansion rate in a way that the standard model, which assumes no such transition, does not account for. None of these are confirmed. Some are not even well constrained by current data. They are live theoretical options that fit within the general boundaries of what the Hubble tension requires, without contradicting other observations. But every new particle or force proposed to solve the tension must also avoid breaking the things the standard model already predicts correctly. Adding early dark energy must not ruin the perfectly correct prediction of galaxy clustering. Adding sterile neutrinos must not distort the cosmic microwave background pattern that Planck measured so precisely. Adding dark radiation must not alter the abundance of hydrogen and helium formed in the first 3 minutes after the Big Bang. The solution space for the Hubble tension is constrained from every direction. Something new is needed. But that something must be surgically precise, powerful enough to fix the gap, quiet enough to leave every other successful prediction intact. That is an extraordinarily difficult target to hit, which is why, after years of proposals, none of them have yet won the field. Right now, in universities and research labs across the world, graduate students are writing dissertations on a problem that has no solution. Postdoctoral researchers are spending years of their early careers working on theoretical models that might explain a 9% gap in a single number. Senior physicists who have built decades of work on the standard model of cosmology are watching that model develop cracks they cannot patch. This is how physics advances, messily, slowly, with enormous amounts of uncertainty and professional risk. The previous generation of cosmologists built the standard model. They verified general relativity with increasingly precise instruments. They detected dark matter through its gravitational effects on galaxies. They discovered dark energy through supernova. They mapped the cosmic microwave background with satellite after satellite, each sharper than the last. The result was the lambda cold dark matter model, a framework that accounted for everything observable with stunning accuracy. The current generation inherited a model they did not build, and they are the ones discovering where it breaks. Young physicists entering the field today face a genuine choice. They can work within the standard model, applying it to new observations and pushing its precision further. That path has clear career benchmarks and steady progress. Or they can work on the Hubble tension and its implications, which means spending years on problems that might not be solved in a single career. proposing theories that might not be confirmed by any telescope currently in operation. History rewards the second path more than the first in the long run. The physicists who worked on the inconsistencies between classical mechanics and the photoelectric effect, or between Newtonian gravity and Mercury's orbit, were working on problems that seemed peripheral at the time and became the foundations of quantum physics and general relativity. Both revolutions came from following small but persistent discrepancies until they cracked open something entirely new. The Hubble tension is a persistent discrepancy, confirmed by the most powerful telescope ever built, surviving every systematic check applied to it, resistant to every known physical explanation, growing more clearly defined with every new survey of the sky. The generation being asked to solve it may be the generation asked to build a new physics from scratch. The Hubble tension does not sit alone. Physics in the 21st century is surrounded by unsolved problems, and they are beginning to connect. The most profound unsolved question in physics is why the universe exists at all. The Big Bang produced equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate each other into pure energy. If the Big Bang was perfectly symmetric, all the matter and all the antimatter should have destroyed each other, leaving a universe of pure radiation and nothing else. Instead, a tiny imbalance survived. For every billion antimatter particles, there were 1,000,000,001 matter particles. That surplus is everything we can see. Stars, planets, galaxies, you. The reason for that imbalance is completely unknown. This problem sits in the same neighborhood as the Hubble tension. Both point toward physics in the early universe that the Standard Model does not fully capture. Both suggest something was asymmetric or extra or different in the first moments after the Big Bang. Any new physics that genuinely explains the Hubble tension will need to be checked against the matter-antimatter problem. A solution that fixes expansion but makes the matter imbalance harder to explain would trade one problem for another. Similarly, the nature of dark matter remains completely unknown. The Hubble tension may be revealing that dark matter interacts in ways the Standard Model assumes it does not. Every proposed interaction between dark matter and ordinary particles, or between dark matter and light, must be consistent with the full body of dark matter evidence: galaxy rotation, curves, gravitational lensing measurements, cosmic structure surveys. Then there is the vacuum energy problem. Quantum physics predicts that empty space contains energy, a restless buzzing of virtual particles constantly appearing and disappearing. The predicted vacuum energy density is staggeringly large. Dark energy, which is the only observed form of energy filling empty space, is far weaker than the quantum prediction by a factor so enormous it strains the imagination. This mismatch, called the cosmological constant problem, is considered one of the worst predictions in the history of physics. Understanding dark energy better, which the Hubble tension demands, may eventually shed light on why empty space does not behave the way quantum theory says it should. The Hubble tension is not an isolated curiosity, it is a thread. Pull it hard enough, and several other unsolved problems in physics start to unravel alongside it. The scientific community is not waiting. Alongside the ongoing debate between Rias and Friedman, a new generation of instruments is already being built, launched, or planned specifically to provide the data needed to crack the Hubble tension. The Euclid Space Telescope, launched in 2023 by the European Space Agency, is designed to map the three-dimensional distribution of galaxies across billions of light years. Its primary mission is to study dark energy by measuring how galaxy clustering has changed over cosmic time. But its galaxy maps will also provide new, independent measurements of the expansion rate at different points in the universe's history. Euclid will help separate whether the early universe and local universe measurements disagree because of a problem at early times or a problem at late times. The Vera Rubin Observatory in Chile is a ground-based telescope designed to photograph the entire southern sky every few nights for a decade. Its legacy survey of space and time will detect enormous numbers of Type 1a supernovae across a wide range of distances. More supernovae measurements at greater precision and across more of the sky will tighten the local expansion rate measurements significantly. If Rubin's supernovae consistently return the faster rate, the case for new physics becomes overwhelming. The Nancy Grace Roman Space Telescope, formerly called the Wide Field Infrared Survey Telescope, is planned by NASA as a follow-up to the James Webb Space Telescope's targeted observations. Roman has a wide field of view that Webb lacks. Where Webb can see a tiny patch of sky with extraordinary depth, Roman can sweep large areas, finding thousands of Cepheids and supernovae across hundreds of galaxies simultaneously. The sheer volume of data Roman will generate will reduce the statistical uncertainty in the expansion rate to levels where any remaining disagreement between methods becomes undeniable. These instruments operate on different timescales. Euclid is already collecting data, Rubin will produce its first major datasets within years, Roman is planned for later this decade. Taken together, they represent humanity's most serious attempt to answer the Hubble tension with brute force observation. The hope is that sheer volume and precision, more galaxies, more supernovae, more Cepheids, measured across more wavelengths of light, will force the true expansion rate to reveal itself unambiguously. The answer is coming. The question is whether the answer will reassure physicists or send them back to the drawing board. Every time physics reached a wall in the past, someone eventually found a door. Classical mechanics described the motion of objects perfectly until experiments revealed that electrons inside atoms behaved in ways that made no mechanical sense. Quantum mechanics was born from that failure. General relativity described gravity perfectly until astronomers discovered that the expansion of the universe was accelerating. Dark energy was accepted because the equations demanded it. Physics has a long track record of finding that reality is stranger than the current model admits, and then building a better model to account for the strangeness. The Hubble tension may be the current wall. If no known modification of the standard model can explain the gap, and if every measurement confirms the gap is real, then physics is standing at the edge of something genuinely new. Not a patch on existing equations, a new framework, a new category of physics that the standard model was never designed to include. History offers a sense of scale. When quantum mechanics emerged in the early 20th century, it did not replace classical mechanics, it extended it. Classical mechanics remained correct at everyday scales. Quantum mechanics revealed what classical mechanics could not see at tiny scales. The two frameworks coexist, each governing its domain. A new physics that resolves the Hubble tension would likely work the same way. General relativity would still describe gravity in the solar system. The standard model of particle physics would still describe the behavior of known particles. The new framework would reveal what the existing models cannot see at cosmic scales, over billions of light years, across billions of years of time. What that framework looks like, no one knows. It might involve extra dimensions of space that only affect physics at the largest scales. It might involve a dark sector of particles and forces, an entire shadow universe of interactions parallel to our own, influencing the cosmos through gravity alone. It might involve something completely outside the current vocabulary of physics, something for which no word or concept has yet been invented. Scientists have been in this position before. Every revolution in physics began with a measurement that would not fit. The Hubble tension will not fit, and that means something is waiting to be discovered. Something that changes the picture of the universe as completely as dark energy changed it in 1998, or as quantum mechanics changed it in the 1920s. The next revolution in physics may already be living inside this 9% gap. You live on a pale blue dot orbiting an ordinary star in one of several 100 billion galaxies in a universe that is roughly 14 billion years old, expanding in every direction, accelerating away from itself, filled with invisible dark matter and invisible dark energy that together make up about 95% of everything that exists. And that description, as vast and humbling as it is, may be incomplete. The Hubble tension is not just a number that does not match. It is the universe pushing back against the story we built for it. Two independent groups of scientists, armed with the best instruments in human history, measured the same thing and got different answers. A Nobel Prize winner confirmed both measurements were done correctly, and the conclusion, stated plainly, is that our rulebook for the cosmos has a missing chapter. Sit with that for a moment. The rulebook that explained dark energy, that predicted the cosmic microwave background with breathtaking precision, that calculated the age of stars and the origin of elements and the structure of galaxy clusters stretching billions of light years. That rulebook has a 9% crack in one of its most fundamental predictions, and nobody knows how to fix it yet. This is what science actually looks like from the inside. Not a library of settled answers, but a living argument at the edge of the unknown. The textbooks that today's students carry describe the universe as we understand it now. At some point, those books will be revised, a new constant will be detected, a new force will be mapped, and the story of the cosmos will shift the way it has shifted before, quietly, permanently, and completely. You are alive in the last era when the full observable universe is visible to us. Galaxies are already crossing the horizon, their light stretching beyond our reach forever. You are alive in the era when the most powerful telescope ever built confirmed that physics is incomplete. You are alive when the next revolution in human understanding is being built. Measurement by careful measurement, in labs and observatories, and equations scrawled across whiteboards by researchers who will likely not see the answer in their own lifetimes. The universe does not care about our models. It behaves according to its own rules. Our job is to read those rules carefully enough to understand them. Right now, we are reading and finding a word we do not recognize. That word is the Hubble tension. And what it means is that the universe is larger, stranger, and more surprising than we currently know how to describe. The search for what comes next is the most important scientific quest of this generation, and it begins with one number that does not match.